Good morning, students. Today we will go forward on our next lecture of basic electrical system. This I think lecture is lecture number 7. Today we will explore the fundamentals of electromagnetism, including its principle, properties, and applications. So, important concept for the today's lecture is electromagnetism. In 1820, scientists discovered that the current carrying conductor are surrounded by a magnetic field. This field can be made much stronger than those of a conventional magnets. The strength of the magnetic field around a conductor can be controlled by changing the current. As the current increases, more flux lines are created, expanding the magnetic field. When current decreases, the magnetic field contracts or collapses. This discovery greatly expanded the practical uses of magnetism, leading to the study of electromagnetics. We will see the relation between electricity and magnetism. Electricity and magnetism are closely related. Whenever an electrical current flows through a conductor, a magnetic field is created. Conversely, moving a conductor through a magnetic field generates electrical current. This relation can be summarized as follows. The first relation is electricity creates magnetism, and the second relation is magnetism creates electricity. From a service technician perspective, it is crucial because wires carry current should always be routed as intended to avoid interference with the other circuits or electronic components. This is especially important when installing or servicing spark plug wires, which carries high voltages and can cause significant electromagnetic interferences. Electromagnets. An electromagnet can be created by magnetizing a piece of iron or steel using electricity. For example, wrapping a nail with 20 tons of insulated wire and connecting the ends to a 1.5 volt dry cell battery will magnetize the iron or the nail, allowing it to pick up tacks or other small steel objects. In the figure, you can see magnetic field which surrounds a straight current carrying conductor. The magnetic field surrounding a straight current carrying conductor consists of several concentric cylinders of flux along the length of the wire. The current flow in amperes determines how many flux lines there will be and how far they extend from the wire's surface. The important concept of left hand and right hand rules. Now, if we want to understand the phenomena of these flux lines, a very important and very simple concept of this left hand and right hand is used in understanding this phenomena. So what is this phenomena that we will see? Now consider flux cylinders which are having a particular direction, just like the flux lines around a bar magnet. The left hand rule is a simple way to determine this direction. If you grasp a conductor with your left hand, with your thumb pointing in the direction of electron flow, that is from negative to positive direction, your fingers curl around the wire in the direction of the magnetic flux lines. You can see in the figures the left hand rule for magnetic field direction. In most automotive circuits, the conventional theory of current, that is from positive to negative, is used. Thus, the right hand rule is applied to determine the direction of the magnetic flux lines. Now, this slide shows a diagram regarding the right hand rule. In this case, the current is flowing from positive direction to negative direction. As we are seeing in our textbooks written by Dr. James Handelman, here in most of the diagrams, it is suggested that the current flows from the positive side to negative side. For this case, we have to use the right hand rule. Now we will see the field interaction and the motor principle. If we want to understand how electrical motor works, then this concept is very crucial. The flux cylinders surrounding conductors interact with other magnetic fields. For instance, if two conductors carrying current in opposite directions, their magnetic fields will also be in opposite directions. Placed side by side, the opposing flux lines between the conductors create a strong magnetic field. Current carrying conductors tend to move out of a strong field into a weaker one, causing the conductors to move away from each other. In this figure, it is properly demonstrated that current with opposing magnetic fields will move apart into a weaker fields. Electric motors like automobile starter motors use this field interaction to convert electrical energy into mechanical energy. If two conductors carrying current in opposite directions are placed between strong north and south poles, the magnetic field of the conductor interacts with the field of the poles, and which results a relative motion between them. In this figure, you can see electric motor uses the interaction of the magnetic fields to produce the mechanical energy. Now you can see this figure. Here is the north pole and this is the south pole. And in between this is a rotor This rotor is composed of these conductors. So this magnetic field of the north and south poles of the stator interact with the magnetic fields of the rotor, and this interaction results into relative motion between these two materials or these two conductors, and this causes this rotor to rotate, and hence mechanical energy is converted into electrical energy. What is a coil conductor and electromagnet? Making several loops of wire around a coil strengthen the magnetic flux density. The flux lines around a coil resemble those around a bar magnet, exiting from the north pole and entering the south. In the figure, you can see the magnetic lines of flux surrounding a coil, which looks similar to those surrounding a bar magnet. An IO core inside a coil conductor concentrate the flux lines, greatly increasing the magnetic field strength. Coils with an iron core are known as electromagnets. This figure above demonstrates an iron core concentrates the magnetic lines of force surrounding a coil. Now, thank you for your attention. In the next lecture, we will continue and explore the other aspects of electrical systems. If you have any questions about today's material, please feel free to ask. Thank you.